Okay, so hello. So last time we defined the Jones polynomial, and maybe I recall that if L is if you have an oriented link, so the Jones polynomial of L is defined as the Kaufman polynomial of A when A square is t minus 1 half. This is a Laurent polynomial in t1 half. And I stated a theorem which said that the Jones polynomial is an isotopy invariant of the oriented link L, so such that it satisfies the following properties. So first there is a scaling relation, which was T inverse VL plus minus T VL minus T T1 half minus T VL0 of T. Here, L plus, L minus, and R0 are three links which are the same except inside a three ball, and they look like this inside. So here, L plus, L minus, L0. And outside the ball, the links are the same. So the value of the Jones polynomial for the unlink is 1. And it satisfies. So if you add to a link a disjunct circle, then the Jones polynomial is modified as minus T1 half minus T minus 1 half VL of T. Okay. Then we can say that the Jones polynomial this is the unique isotopy invariant of link invariant of oriented links, which satisfy the property A and B. And we also can say that if L is an oriented link with, let's say, m components, then we have that the Jones polynomial is Laurent polynomial in T if the number of components is odd, and it is T1 half times a Laurent polynomial in T if m is even. Okay. So last time I stated this theorem. So let us prove it. Okay. So we have that. First, that the Kaufman polynomial, we have already seen that it is an isotopy invariant. And so the same is true for the Jones polynomial. Oh, so this is clear. Now, let us prove the first property A. So recall that, so consider let D plus be a diagram of the link L plus and we consider diagrams D minus D0 of L minus and L0, which are obtained from the diagram of L plus by changing obtained from D plus. So diagram for D minus, we change the crossing. Or changing, or let's say, or smoothing the crossing. Okay. So let us recall that the Kaufman polynomial is defined using the bracket polynomial. So what do we have? So if I take the bracket polynomial for the unoriented diagram D plus. So this is bracket polynomial for this one. So this is A. So time plus A inverse time and not the bracket polynomial for D minus. This is the bracket polynomial for this one. So it is here A plus A inverse. So what do we have? So we want to remove this bracket. So what can we do? We can multiply by A plus A D plus minus A inverse D minus. It is equal to A square minus A minus 2 this is equal to A square minus A minus 2 D0. Okay. So now to obtain the Kaufman polynomial, we need to multiply by power of A using the raised number. So we have the raised number of D plus is the raised number of D0. So So plus 1, and the right number of D minus, the right number of D0 minus 1. This is clear. So we have this relation. So if we multiply this with what we know, so minus a third power minus omega d0, which is again minus a third power minus omega d plus plus 1, which is minus a third omega d minus 1. Okay, we obtain. Okay, so here a times minus a cubed times, so minus a to the 4 times KL plus of a minus a to the 4, so plus K, the Kaufman polynomial of L minus A is equal to A squared plus A minus 2 K L0 of A. So now, if we change the variable and put a squared is t minus 1/2, so what we obtain? We obtain A. We obtain the relation A. Okay, so we have proved A. So let us prove the relation B. So clearly, so the joint polynomial for the unlink, it is so we have that the Kaufman polynomial for the unlink, it is minus a cubed times the number, the right number for this diagram for the unlink times the bracket polynomial of the unlink, and so it is minus a cubed 0 times 1, it is 1. And thus, the joint polynomial of the unlink is also 1. So this is clear. Okay, so the third relation is, again, follow from the property of the bracket polynomial. So property C. So let D be a diagram of L. Okay, so what is the right number? So if I add a circle, this is a diagram of the disjoncture of L and the circle. Now, the right number of the disjoncture of D and the circle is just the right number of D. Now, the bracket polynomial so this is a bracket polynomial, and we know from the bracket polynomial this is equal to as far as I remember, probably minus a square minus a minus 2. See? And this implies that the Kaufman bracket of L is minus a square minus a minus 2, the Kaufman bracket, the Kaufman polynomial of L. And this gives the property setting e square t minus 1/2. Okay, so we have verified that the Jones polynomial satisfies A, B, and C. Now let us prove that this is the only polynomial invariant, isotopy invariant of oriented links that satisfy A and B. So let's call it J, B, E, an isotopy invariant of oriented links satisfying A and B. So the scaling relation, A is the scaling relation, and B is the value at the unlink, unknown is 1. Okay, so first, so G satisfies C. So let us prove this. So why? So let L be an oriented link. Consider an oriented link L. So L, so you can consider a strand of L going downwards. It is isotopic to this one. It is isotopic also to the other one. And here we have L plus, L minus. So L plus and L minus, if I modify a strand of the link like this, are both isotopic to L. And L0 is just, so this is isotopic, it's just the disjunct unit of L and a component. And thus, if we apply A for the invariant, J, so property A, what does it give? It gives that T inverse TL plus minus T L0 L minus equals T1/2 T minus 1/2 T L0. So this gives, so L plus LL are both isotopic to L plus and L minus are isotopic to L, so we take T minus 1 minus T TL is T1/2 T minus 1/2 TL disjunct unit circle. And so G L disjunct unit circle is what is minus t minus 1, so t 1 half minus 1 half is the t 1 half. So this is C. So an invariant which satisfies A and B also satisfies C. And in particular, what can we say? B and C gives that. So for the unlink, J4, if you take the unlink with M component, you apply M minus 1 times C, you get minus T 1 half. Minus T minus 1 half M minus 1 times J at the ending, a knot, which is 1, so we obtain this. Okay. So, okay. So now, and this is particular the value of the Jones polynomial. Okay. So, our isotopy invariant and the Jones polynomial coincide for the unlinks. Now, consider an oriented link L and D be a diagram of L. Let's say it's the number of crossings. Let's call it N. So what can we say? We want to change the crossings of D to obtain the unlink. So, particular, there is a finite sequence. Let's call it D1 decay of link diagrams, of oriented link diagrams. So with N crossings such that di plus 1 is obtained from di by a crossing change. So we just change the overpassing and underpassing. So the first is our diagram D of our link, and the last is a diagram of the link. Okay, so why can we find this? So, okay, let's see on an example. So we have of link L, and we consider a diagram. So we have a projection on a plane. So our link is oriented. Okay, anyway. So we have our oriented link L, and we consider a diagram on the plane. Now you forgot, so this is D1. You forgot the crossing information. And you obtain this, a diagram with no crossing. And then from this, okay, maybe I make it more. Okay, well, anyway. Then you choose a point, for example, this one. And you start from, let's call it. And you now follow the link always going up. So you have okay, I took this orientation, so you follow the orientation. Going up, so it's difficult to. I just made, okay, let's take the orientation. It's more easy to do this. Okay, so I start from this. Like this. Okay, and I come back. So here, we start from this point. Maybe I should write like this. So what do I? So this corresponds to this corresponds to this, and this. So the idea is just you go around this this curve going up. Clearly, it projects onto this curve. And clearly, if you go up and then come back, you have an unlink here. And then if you project again this, what do we obtain? Now, if we project, we have changed the crossing. So let me. Let's write it like this. Okay, so now if we project, we just have the upper crossing here. Then this is upper here. No, upper like this. Okay. And you see this is a diagram of the unlink. And this is your diagram decay. And clearly, you can find, you can obtain this diagram of the unlink from this one by a finite number of crossing changes. Okay, and if you have several components, it is the same. Okay, so we can find a sequence of, so we can obtain the diagram of the unlink by changing crossing of D. Okay. Now, if I denote B Li, the oriented link, defined by the diagram Di. So L1 is L, and Lk is the unlink.
So if you had more components in the beginning,
Okay.
you would at the end also have more components, or you would take only one component in the end?
No. If you have more components, let's say one more here, one more. You go around the first component, then you go around. Okay, so here you have the diagram. You take one component. You go around, you have this. Then you go above, and you take the second component. Like
so you end up with more components in the end?
Yeah, at the end you have the same number of components. No, at the end, yeah, you have a link.
Yeah, or unlinked?
Unlinked.
Okay, yeah, okay.
Okay, so if you have several components, you go around each component one over the other. Okay, so now, what do we have by A? The property A says that Li and Li plus 1 and Li differ by a crossing. So we have T j of Li minus T j of Li plus 1 is T 1/2 minus T minus 1/2 G of Li prime, or it depends if the crossing is positive or negative, T G Li plus 1 minus T minus G Li is T 1/2 minus T minus 1/2 G L prime I. And here, G L prime I is an oriented link having a diagram with less than the number of crossing of D was M or N. I do not remember. N less than N crossing. So M or N? M. Okay. Okay. So since now we know the value of for the unlink, we can compute inductively what G, so this is G of Lk. So using G of Lk minus 1, G of Lk minus 2, G of L1 is G of L. Using this kind of relation we obtain here. But here we know, so the condition is provided we know we know GL prime for L prime for oriented links L prime which have which have diagram with less than n crossings. If we know how to compute the value of J for links having diagram with less than n crossings, we know how to compute GL. And so we know how to compute G of a link having a diagram with n crossings. So inductively, we know how to compute G for every link. And so, since for the unlink, it is the same value as of the Jones polynomial of the unlink, we deduce by induction that for any link, we have this. So we have proved the uniqueness of an isotopy invariant verifying A and B. Now it remains to prove that if the number of components of L is odd, it is a Laurent polynomial in T, or 1/2 T1/2 times the Laurent polynomial in T if the number of components is even. OK. Alors. So for the unlink, I recall that for the unlink with M components, we have computed already. It is minus T1/2 minus T minus 1/2 times A minus 1. And here, this is T M minus 1 over 2 times minus 1 minus T minus 1. M minus 1. OK. This V is belong to Z T is the Laurent polynomial of T if M is odd, and in T1/2 the Laurent polynomial of T if M is even. So for the unlink, it works. So now we consider let L be an oriented link. So we know by the above, GL can be computed. So can be computed. So this is the Jones polynomial from V the unlink using this chain relation A. This is the computation above. We made this above. This is the same computation. So consequently, what can we say? because we only need to prove the, it suffices to prove the property that if the property, so the property of belonging, this or this depending on the number of the parity of the number of components. If the property hold for 2 of the 3 links L plus N minus N0, then it holds for the third link as well. Okay. And this is because VL is computed using the scan relation from the unlink. And for the unlink, this works. Okay. So here, so I recall that L plus this one, L minus this one, and L0 is 1. So we denote by, let us denote by M plus M minus M0, the number of components of this link. So what can we say? What we need to find some relations between M plus N minus and M0. So there is an easy relation. How can we compare M plus and M minus? The number of components, if you change the crossing here, is same. So M plus is M minus. Now we need to compare M plus with M0. So there are 2 cases to consider. So depending, so let's say that it depends if the strand of the crossing, so the strand of the crossing belong or not to the same component. So in the first case, so if the, so let's take okay, so I have L plus, and if they belong to the same component, so outside the ball, what happens? If they belong to the same component, we have something like this. And this gives that L0 is like this. And so we have M0 is M plus minus 1. And the second case, this strand does not belong
Sorry, it's plus 1.
sorry
Is it plus 1? The M0 is M plus 1?
M0, yeah, plus 1, sorry. Yeah, there is one more component. Thanks. So if they do not belong to the same component, so necessarily we have things like this. So this is L plus. And so L0 is, so inside the ball we have this, and so there were two components, is there one component, so M0 is M plus minus 1. Okay? This is clear. So finally, I will finish. So in particular, so we have that M plus and N minus have the same parity, and M plus actually they are equal, and N0 have distinct parity. And so we can conclude that T VL plus minus T inverse VL minus is T1 half minus T minus 1 half VL0. And so we can show. So see if the parity of M0 is, let's say, even. So this is 1/2 times a Laurent polynomial of T. So this product is a Laurent polynomial of T. And thus if Vn minus or Vn plus are a Laurent polynomial of T, the other also. So we can conclude by induction that the property holds. Okay. And maybe we finish, make a break. So after the break, we will see another way to define the Jones polynomial using so-called operator invariants. And then, maybe I will not have time today, but next time we will see how to obtain solutions for the operator invariant method using quantum groups. Okay. So now we will see another method for defining the Jones polynomial. So I think the third section, and let us go. So the Jones polynomial as so Jones polynomials as standard operators. Okay. So if I first define the notion of tangle. Basically, they are like links, but we allow free ends. So let's say a tangle with k inputs, L outputs, and M circle components is the image. Let's call it T the image of a smooth embedding. So we want to embed some disjoint unit of the interval. So I will denote by I is the closed interval 0, 1. So disjoint unit a number of circles. So inside R2 cross 0, 1. So what do we have? Here we have so M circle component. And the number interval is K plus L over 2. So K plus L must be even. So this image, so we impose conditions. So we send this must send the interior of the intervals and the circle in the interior of these three manifolds, also R3 cross. So the open interval, do you denote like this or like this? It depends. I don't know. How do you denote it? Like this or this? Second one? Okay. So only the endpoints of the interval are sent.
Wait, is it R2 or R3?
So yeah, thank you, R2. Are sent at the boundary. These are the plane R2 cross 0, R2 cross 1. And also such that so we need that the tangle T meets the plane R2 cross 0 orthogonally along the point let's say I 0, 0, well, with I between 1 and K. And these points are called, let's call them inputs. And T meets R2 cross 1 orthogonally. Along the points, let's say I 0, 1 with I between 1 and L, and these points are called outputs. Okay, so let's see an example. So we have two planes. So these are R2 cross 0, R2 cross 1, and let us depict the tangle. For example, so let's say, I don't know. Let's say this one. Okay, and let's add some components here, for example, and another component. Yeah. So what is it? It is maybe I can add to be short. So for shortness, we call such a tangle a KL tangle. The definition. So this is what here? How many? So we have 4 inputs, 2 outputs, so this is 4 2 tangle with so here 2 circle components. And there is 3 intervals. So the first one from here, the second one here, and the third one here. Okay, so, and we say that 2 tangles are isotopic if they are related by an isotopy not of R3 as falling, but of R2 cross 0, and we want that this isotopy is constant on the planes. So we can deform the space inside. So this isotopy is constant on R2 cross 0 and R2 cross 1. Okay. Maybe I'll make a remark. So what is a 0-0 tangle? It's just a link. Okay, so as for links, we can define diagrams of tangles. Let's say a tangle diagram it's an immersion. Let's say is the image T of a smooth immersion of a joint copy of interval and circle into R cross 0, 1 sending the interior of the interval and the circles inside R cross 0, 1. And such that. So as for link diagrams, we only consider transversal double points. There is a finite number, so let's say there's a finite number of transversal double points called crossings. And at each crossing, once strand is chosen and called overpassing. It's like for link diagrams. Okay. So we have finitely many crossings, and as for tangles, so D meets R2 cross R cross 0. So orthogonally along the points I0, I should say a diagram with K inputs, L outputs, and here you have K plus L over 2, K plus L even, and they meet R cross 1 orthogonally along the point I1. Okay, so an example. Let's say, so for example, I don't know.
So sorry, do we go from 0 or from 1?
Sorry? For 1, thank you. If K or L is 0, there is no such point. It does not intersect. Thank you. Okay, so you have R cross 1, R cross 0. And so, for example, you to consider it's like and so this is K plus L must be even. Okay, thanks. So this is a 3-1 one tangle diagram with 2 circle components. Okay. So it's exactly the same thing as for link, but we have okay. And again, two tangle diagrams are isotopic if they are related by an isotopy of R cross 0,1, which is constant on R cross 0,1. And we can define an oriented tangle. So let's say oriented tangles and oriented tangle diagrams are tangle diagrams whose components are oriented. It is quite clear. This is an image by an embedding on immersion of oriented interval and oriented circle. And we have what? Clearly, if you have a tangle diagram, it defines any possibly oriented tangle diagram D defines an oriented tangle TD. If our time it is well defined up to isotopy. A tangle diagram defines an isotopy class of tangle. This is clear. You just use the overpassing information to embed the diagram in R2 cross 0,1. And also, we have that any oriented tangle has a diagram, which means there is an oriented, let's call this T, this tangle, oriented tangle diagram D, such that T is isotopic to TD. This is clear. So, and as for links, we have a version of the Reidemaster theorem which says that two maybe oriented tangles. So let's say, okay, two. They are isotopic if and only if their diagrams are related by a finite sequence as you can imagine, plain isotopies and write the master move of isotopies of R cross 01, of course constant on the boundary, and of write the master move or oriented write the master moves. Okay. So if we want to define invariants of tangle, we can use this theorem. But now the advantage of tangle with respect to links are we have more operations. So let's say 1, 2, 3. I will define what are sliced tangle diagrams. Okay. One of the advantages of, as I say, of tangle, we have the operation. So we can define, let's say, the tensor. So what operation do we have for links? We can, for example, use the disjoint union. So generalization of this for tangle is called the tensor product of tangles of, let's say, KL tangle with, let's call it T, with a K prime L prime tangle. T prime is what? Is the K plus K prime L plus L prime tangle. We denote it like as T. So T prime, it is defined as follows. Take T. Take T prime. Just here you have K input, L output, K prime input, L prime output, and so you obtain a K plus K prime, L plus L prime tangle. Just juxtaposition of tangle. And for link, if T and T prime are links, this is just the disjoint union. Okay. But now we have another operation. We can compose tangles, contrary to links. And this is one advantage. So the composition of, let's say, KL tangle, let's call it T1, with a LM tangle T2, T2 is the KM tangle T2, T1. What can you do? T1, you can put L output, but you can put T2 on the top of T1. And of course, then you take some OTC of factor 1/2 to come back to the R2 cross 01. Sorry? T1 is KL and T2 is LM. Oh, okay. And what you obtain is a KM. You read from bottom to top. No? Okay. So we have these two operations. Now, I want to define what is a slice. So, a slice, let's say, so is a tensor product let's say finite tensor product of the following, let's say is a tensor product of a finite number of a finite number of the following, let's call elementary term. Elementary here we consider only oriented case, elementary so we consider this one, two crossing downwards, oriented downward, and some cup, the two cups, and the two caps. Okay. Let's see an example. Yeah.
So for the composition, you also need to have the to orient it.
Yeah. So for the orientation.
For the composition.
Yeah. Good question. So the remark is for the oriented case, the outputs of T1 and inputs of T2 must be oriented coherently. So if we have orientation, the orientation when you want to compose must be for the output of T1 and input of T2 must be coherent. Thanks. Remark. Okay. Okay, let's see an example of a slice. So example. So particular a slice S, let's say so here this is so see here we have 1, 2, 3, 4, 5. 1, 2, 3, 4. Is for example, maybe I should let's say is 3. 3, 7 oriented tab. Okay. So just a juxtaposition of elementary tangle diagrams. Elementary tangles.
So is there a reason why there is only one orientation of the crossings?
Yeah, I explain because, so, since you, so I come back later, but maybe a remark is, for example, if I choose, let's say, this one, you can decompose it like this. Okay. And this is part of the proof of the next lemma, actually. So now, a sliced tangle diagram is what? Is the oriented tangle diagram let's say an oriented tangle diagram obtained as the composition of slices. And maybe there is the following property. Any oriented tangle is isotopic. So, any oriented tangle, let's say, tangle diagram. So let's say isotopic tangle diagram is isotopic to a sliced tangle diagram. And why? This was your question, because, so let's call it the proof here.
Sorry, what's the statement?
The statement is, if you take a link diagram, a tangle diagram, it is isotopic to a slice tangle diagram. Okay? And the proof is that we can transform a tangle diagram so that its crossing, so by isotopy, so that its crossings are oriented downward. And this is, for example, an example here. We just locally we rotate. Another example, for example, this is isotopic to okay. And so you can imagine this is the proof. Let's see an example. So, So, for example, I take the threefold, so I cut it. For example, I have something like this, and I orient downward. So here, this is something like this. Here it is up. Here it is like this and like this. Okay. So here it is isotopic. So we want to use this tangle as a slice, this tangle diagram, one tangle diagram, as this sliced one. So what can we do? If I do not make a mistake. And here, everything is oriented downwards. And so what are these slices? Yeah. Here we have the slice. So this tank diagram is a composition of these 5 slices. Okay. And maybe I state a theorem which relates two slide diagrams. And we will use this next time to construct operator invariance. So this is a theorem from Touraev in maybe 88. Two sliced diagrams represents isotopic oriented tangles. If and only if the slice diagram, they are related. By a finite sequence of the moves T1, T8 or 9, I don't know. And I will define these moves. So we need moves between in the class of sliced diagrams. So what can we do? We can by the Reidemeister theorem, we have isotopy of the plane and the Reidemeister move. But in this case, isotopy of planes can be decomposed using T1, T2, and T3. So T1, you have a diagram D, and you have a trivial diagram, tangle diagram. Trivial, I mean just something like this. This is trivial. So this is the same as D. And you can, if you add the trivial tangle diagram, you do not change the diagram. Of course, D and D prime are slice diagrams. So the second move is, what can you do? You can slide trivial D prime trivial. You can slice the diagram, which are not linked. Okay. So this is plane isotopy preserving critical points which, with respect to the 8 function. And so now how can we create or delete critical points like this? And or this, depending on the orientation. Okay. So this relate isotopies. Now, the first move, I just give the move and I finish. So to obtain a slice diagram, we need to rotate some crossing so that the paths are oriented downward. So this indeterminacy is controlled by this move. This one we can rotate in 2 manners. So the first one like this, but we can also the other way. And of course, we want this move must be true. T5 is just write the master 1. T, let's say 6 is write the master 2, oriented downward. So I recall for the oriented write the master 2, there is also another version. We cannot do this, so we have to transform, let's say, and in this case, the crossing are oriented downward. So this corresponds, T6 and T7 correspond to write the master 2, T1 to write the master 1, and T8 is just write the master 3, oriented downward. Okay. And 2 slice diagram define the same tangle if they can be related by these moves. Okay, and we will see next time how to use this theorem to construct invariant of tangles, which for links will give the Jones polynomial.